Alright, so in the interest of time, I've already drawn out ray diagrams for every problem. Unfortunately, I did them in pencil because I knew I was going to have to be making eraser marks here and there. Anyway, I can walk through it. This is the convex mirror for problem 7. And I don't think we weren't supposed to really answer the question. He just wanted us to do the diagram, but I came to an answer anyway. I used old Trusty here to get a real nice diagram. Yeah, it's a nice big ruler. So it's pretty accurate. It's not exactly to scale, but I was able to use factors of 12, I think I used. So anyway, here's the object, and the rays that are coming out, this first ray just hits the mirror parallel, and it's reflected off as though it came from the focus over here on this side. Another ray, it's going straight towards the center of curvature, way over here, and it is reflected back exactly the path that it took to get there. And then the last ray is the one that appears to go towards the focus on the other side, and that one is reflected parallel. So where these ones converge on this side, these dotted lines, that is where the virtual image is created. And I did measurements. It ended up being a little bit off. I know that my drawing was accurate. It ended up being a little off from the math. The math had it being as the image distance is -12, and I measured -13.6, taking into account my scaling. So the magnification, on the other hand, ended up being 0.4, and since I drew this big one as 3 centimeters, this one came out as 1.2, which is exactly 40%. I thought that was cool. Anyway, that's the first one. This is for problem 30, the convex, or the converging lens, rather. And this problem was, okay, so we just have an object way over here, and it's going to make this little real image back here. We know it's a real image because it says that it forms on a screen behind the lens. So only a real image is going to form on a screen. So I had to do some math to get the numbers. I got the focus to be 6.4 centimeters, just using the equation. The 1 over P plus 1 over Q is 1 over F. So F ended up being 6.4, and then once I had that, I could draw the diagram. And so what I have is this big old arrow over here. This parallel ray gets refracted down towards the focus on this side, through the focus. It's a real light beam. That's not a dotted line. Then I have one, it passes directly through the principal axis right here, and then it passes undeflected. And then the last one, it goes towards it goes through the focus on this side, and then it passes parallel to the principal axis over here. So these are all real light beams, and this is a real image that ends up being inverted. And this one, I measured it, it ended up being exactly what the equation said it would be. This is exactly at 8. And again, the magnification was right on. So that's 30. This one's 31. This is the one with the nickel, and it tells you that the nickel has twice the diameter. So you know that it's magnified 2 times. And knowing that, they give you the image distance 2.84, ends up being a negative image distance because it's a converging lens. and the image ends up in front of the lens. So we know that that's going to be a negative image. And doing that, we can get the object distance to be 1.42, and that means that the focal length is 2.84. So this image is actually on a focal point. And the way that the rays work is that this one will go right, it's kind of small, so right from the top of the arrow, it'll seem like it came from the focus over here, straight up till it hits, and it'll go parallel. So then we could draw a parallel dotted line back. Then a ray will come straight out of the top, parallel to the principal axis, and that will get refracted down through that focus. And we can draw that dotted line back up. And then, just like the last one, a ray will go right through this point here at the principal axis, and it'll pass undeflected. And then we can draw a dotted line back there, and they all converge back here. And this is a virtual image. And that is the path of light for that. The next one problem wasn't in the book. It said a concave mirror with a focal length 40 centimeters. And you wanted to know the object position that would give us a image that is upright and 4 times the size of the original object, which is this one. So I started with the magnification. 4 equals negative Q over P. I know it's kind of blurred, you can't see it, but I'm talking it through. So Q equals negative 4P. And then, now that we have Q, I substituted it in, and that would come to 120 equals 4P, P equals 30 centimeters. So we know the object distance is going to be 30 centimeters, and then 120 is 4P, and negative 4P is Q, so Q is negative 120. So the image distance is negative, so this image should be virtual behind the mirror and back of the mirror. So I've got a little drawing. I don't think you wanted a drawing for this one. I think you just wanted to know the position, but I drew it anyway just to verify. So the path of light, it comes up from the focus over here. And reflects parallel. That's how I get that dotted line. This one comes right through the center of curvature. It gets reflected right back on itself, but a dotted line can be drawn up here. And then one that comes, there's a light, ray of light that hits it straight on, parallel. Did I already talk about that one? No, this is, well, you can see what I did. And it converges back up here. The measurement didn't actually turn out how I wanted it to. It ended up being a little bit far left. It should have been 120, which is right here. It ended up being 98.5 right here. These are in millimeters. Not centimeters like the problem, but, you know. So I don't know. The magnification, on the other hand, ended up being pretty exact. This is 4 times bigger than that one, which was 1 centimeter. So it ended up turning out pretty good, but anyway, these are my numbers. The object distance is 30 centimeters. And then the last problem is here. Alright. So I drew a pretty nice picture for this one, so I'm fairly certain that it's accurate. We've got this thing over here that's 14.4 centimeters to the left of this converging lens. And so using these light beams, these rays, they're going to converge into a real image right over here that's inverted. And it turned out, it surprised me mathematically that it was actually going to be larger than the original image. The magnification is negative 1.25. So this is actually 1 1/4 times bigger than that image over there is. And I measured it. It really is. So anyway, from that, this is the new object now, and the rays of light are going to hit this diverging lens, and you can see where the light's gonna converge. This one, it'll hit straight. I'll do it with the pencil. This one will go straight out. It'll hit the diverging lens, and it will deflect down this way, as though it came from the focus, which is right here at 3 centimeters. And a dotted line will go back up that way. This one will, how do I do this one? Oh yeah, this one appears to, well, it's going in the direction of the focus on the right side, and it gets deflected parallel. So we draw that line back this way, dotted line. And then this one, the top beam, goes right through the center here at the principal axis, passes undeflected. So those all converge right here and form this smaller image that is not inverted compared to this one. So that's why the magnification ends up not being negative for that one. Ends up being 1/3. Just negative Q over P. So negative 2 over 6. Oh, yeah, I guess I should show the math over here. This one gives me my first Q1, the first image distance to be 18. So since this is 24 centimeters between these two, I know 24 minus 18 gives me 6. So this image is now 6 centimeters from the diverging lens. So knowing that, I can do another equation, 1 over 6, the new object distance, plus 1 over the new Q, equals negative 1 over 3, because we know that the focal length for the diverging lens is negative 3, and that gives a Q negative 2. So the image distance should be in between this focus at negative 3 and the lens, and it is. It ends up being right there at negative 2. So all the magnification turned out correctly. To get the total magnification, you just do multiplication of these two magnifications, and it comes out to be right. That should be negative 1.25 times 1/3, so negative 0.42. And that means that it is inverted compared to the original image, and it is 42% of the size. And let's see here. That means that the image is 2 centimeters to the left of the diverging lens. I think that's how you wanted the answer. And that is it.